That was a whole lot of analysis, code, graphs, and number magic in a short amount of time. Maybe some of the stuff felt kind of abstract, and that's perfectly okay. After all, what we have seen so far is just a toolbox, and with only little focus on concrete algorithms and data structures. However, we will use the concepts intensively in the next modules. Let's take a look at what we have learned so far. First of all, we saw that while measuring time using a stopwatch can give insights of a specific execution on a specific type of hardware, a method that is more suitable for comparing algorithms is to count instructions. The observation was that we can always come from instruction count to execution time by multiplying with some per instruction time. The instruction counting also has the benefit that it is independent on the hardware executing the program. Given an expression for the number of instructions needed to run a program for a given input, it makes sense to focus on the nature of the curve it represents. By looking at the curve, we can get an idea of how the execution time evolves for larger input sizes. After some experimentation, we saw that constants did not have an important impact on the nature of the performance curve. And this is often a difficult thing to accept. And to be fair, we shortly saw an example where these constants actually had an effect for sufficiently small input sizes. When first you get this ignoring of constants under your skin, it gets much easier to get an overview of the worst case performance of a function, but it takes some practice. We saw three different notations for complexity. The big O notation denotes an upper bound of the actual performance, a worst case. That is, the actual performance is guaranteed to be somewhere below the curve. And maybe you can remember it by the rhyme O below. The big omega, on the other hand, denotes the lower bound of the actual performance. That is, the actual performance is guaranteed to be somewhere above the curve. You may remember it by considering the omega character and the horizontal line fragments that constitutes the feet of the character. Then all the interesting things happens above that line. And then we have the big theta, which denotes the actual complexity. You may remember it on the horizontal line of the theta character, which stays exactly in the middle of the upper half and the lower half, just like the actual performance is bounded within the lower and upper bound. We took a look at how to calculate the complexity of recursive methods and found that a good strategy may be to consider a bound on the number of recursion steps, or folding the recursion out, and then considering the complexity of the internals of each recursion step. Last, we shortly covered the concept of amortized analysis, which concerns the complexity of executing an operation multiple times. Here, the cost of possible occasional housekeeping may, sort of, even out, even though it results in certain spikes now and then.